We have one final point to make before we're finished discussing heat engines, and that is Carnot's theorem, which I've mentioned now a couple of times. The theorem that says that the Carnot cycle or Carnot engine is the most efficient engine that you can envision. And what exactly do I mean by that? Well, in this video, which is a supplemental to the main videos, we're going to make that point as clear as we can. So let's again look at the Carnot cycle. So here it is in PV space. Remember that we're going to want to go counterclockwise in this space. Here, the steeper two curves are adiabatic, and the shallower two curves are isothermal. Now, in video 3, we also looked at this same cycle, but in ST space. And to remind you of what that looked like, it was just a rectangle. Good. And now should be going clockwise. Okay, let's discuss something I referred to in the last video but never worked out, which is how do we use two forms to calculate the heat? So we know that Q, if this is the cycle C, Q is equal to the integral along C of T ds. But since C is the boundary here, in fact, it's the negative, since C is the negative boundary here of a region curly S, we have that this is equal to this integral over curly S of TDS, and therefore is equal to the surface integral over the whole region S of dTds. And should have put the minus in there and the minus there. Now, using what we've learned about the wedge product and the exterior derivative, this is the integral over S of dt wedge ds. But in fact, oh, and forgot the minus sign again. But in fact, because we're in ST space, not TS space, we need to flip the order here. So this is plus the integral of ds wedge dt, which means it's the area inside of region S in TS space or in ST space. Good. So total heat in a cycle equals area inside of cycle in ST space. Okay, there's one more thing to think about, which is evaluating each of these heat integrals. So for instance, if this is section 1, this is section 2, this is section 3, and this is section 4, then the heat that enters in section 1 can be calculated by integrating TDS over that section. Let's do that. Now, let me draw this out again on the right here, and we can think about what this means. I'll just draw section 1 in this case. Well, this is the integral of t as a function of s in st space. And so, really, it's the entire area under here. Very good. So when is heat coming into the system? In st space, it's actually quite easy to see. Anytime our curve t as a function of s is headed to the right, then heat is coming into the system. Anytime it's heading to the left, then heat is going out of the system. And anytime it's heading vertically up or down, no heat is entering or leaving the system, since we'll be on an adiabat in those cases. All right, so without further ado, now let's state Carnot's theorem. Suppose a heat engine reaches minimum temperature Tc and maximum temperature Th. Then its efficiency, which we'll call eta, satisfies eta is less than 1 minus Tc over Th, which we know is equal to eta for the Carnot cycle. Good. Let's draw that out in a figure. Okay, so let's draw in Th in blue, or sorry, Tc in blue and Th in red. And we know that we have some cycle which reaches a maximum temperature of Th and a minimum temperature of Tc. And we know that if it's going to be an engine, it should be going clockwise in this space on net. Notice that there is this little region in here which is actually going counterclockwise. Okay, let's offer a visual proof of Carnot's theorem. Mostly visual. I might talk through some bits as well. The easiest thing to get rid of is these little self-intersecting loops, regions where we're going counterclockwise. And why is that? Well, if we have any region that's going counterclockwise, we can excise it from the main loop and look just at its efficiency. Notice that it has a negative area. Area less than 0, considering that it's going the wrong way. Oops. But it does contribute some heat. Namely, heat is going in for the part of the counterclockwise loop where we're going to the right, the part at the bottom. So positive heat. And what this means is that we're contributing negative net heat, but positive in heat. So since the efficiency is equal to 1 minus, is equal to minus W over QH or Qin, which is then equal to Q over QH, since Q and W are negatives of each other by the first law. Anytime we're contributing a net negative heat, but a net positive heat in, we're sort of necessarily lowering our efficiency. Okay, so now we can restrict ourselves to thinking about cases in which we have no self-intersections. We're bounded again below by Tc, and above by Th. So now this is a positive area, and we want to know how to maximize this area that I've marked inside while keeping as low as possible the total of the heat in, which remember is being added anytime we go to the right. So that means it's everywhere between these points that I'll mark A and B. So just to clarify again, eta is equal to the green area divided by the green plus the red area. Just for accessibility, I'm going to mark the colors here as well. Okay. Now, how can we maximize the green area here? Well, it's very clear we want the green area to fill in anything above this blue dashed line here. Anything else is just wasting some space. So let's show that that is going to increase our efficiency. Also got to label my axes. Don't want anyone yelling at me. Okay, so we should definitely fill in everything down here. So now all of this up here is contributing to net heat in without adding any more. Sorry, all of the green part now, everything above the blue dashed line, is contributing to the total heat without contributing any more to the heat in. Good. Now we need to worry about the region up here. So these are regions that are beneath some part of this upper line here. So they are definitely contributing to this lower rectangle down here in red. But these regions over here are not contributing to the net heat. But if they did, notice that our efficiency would go up because we wouldn't be adding to the red region, but we would be adding to the green region. But once we fill that in, look what shape we've arrived at. It's the Carnot engine. Good. But since each of these steps increased efficiency, or at least didn't decrease efficiency, we know that the efficiency of this final system is greater than or equal to the efficiency of the original system. And actually in Carnot's theorem, I should have had this be less than or equal to. Mm. And that completes the proof. Hopefully that this proof gives you a little inclination about why Carnot's engine is important, but more than that, gives you a sort of visual way to think about the heat that enters or leaves a system in ST space. Thanks so much for watching, and I'll see you in the next one. Bye-bye.